Now we will look at a numerical example which will illustrate whatever we have discussed so far in terms of expressions, but before going to that I would say a mathematical or theoretical example. What is shown in the right hand side is a figure where whatever we discuss is more practically applied. What is shown there is a bar, a vertical bar, and subject to a compressive load, compressive because both are acting towards each other, it is a compressive load. Okay. Now based on the equations what we have derived, we can find out that at 45 degrees you have maximum shear stress, maximum shear stress. Okay. Now if the material stress which it can withstand is less than this maximum shear stress, then what happens? It breaks along this 40, look at this, it has broken along a 45 degrees axis, 45 degrees plane. So you can prove that based on this Cauchy's law that maximum shear stress occurs at an angle of 45 degrees, because how can we do that? Our n can be any plane, so find out the n or angle at which you have maximum shear stress, and practically you can observe that when you keep increasing the load and if the maximum shear stress exceeds the allowable shear stress, usually materials have some limit for shearing direction and for normal direction. Okay. The normal values may be more, but shearing values may be less. So if your shearing stress, resulting shearing stress along 45 degrees, if it exceeds, then it starts breaking. Okay. That is the example shown here. So if you look at solid mechanics book, a lot of such practical examples are given. Our objective of studying solid mechanics is to take principles from here and apply to fluid mechanics. So we are not discussing in detail about such examples. What we will do is a more mathematical example, theoretical example, which will clearly illustrate what we have discussed so far. Okay. So that is why this example is shown in this slide. There is no relationship between this diagram and this example, apart from that both are applications. Okay. Okay. Now suppose that the stress tensor at a point in a solid is given by this, let us say, matrix. Okay. We are given all the 9 components of stress tensor. Then we are asked to calculate the following: compute the stress vector at point P. What is to be noted is stress tensor at a point P is given. We are asked to find out stress vector at point P for a surface with orientation n, which means the normal vector to the plane is given to us. Now for the surface, which means that the surface which is referred above, determine the normal component of stress vector, which is the normal stress. Next is compute the 2 tangential components, meaning the shear stresses. Okay. Remember this was our objective, to calculate these values. As I told you, the first step was done through Cauchy's formula. Second step is more easily done through vector algebra, that will be illustrated in this example. Okay. Second step is we have stress vector components along x, y, z, we have to have components along n, s1, s2, we will see that now. Okay. What is given to us? Let us understand that in 2 ways. Remember we had this stress element with 9 independent components. We had 9 more which are same as the other 9, and earlier we had expression for tau, just introduced variables. Now we have numerical values for them in this example. What is given to us? This value, let us say tau xx is 2, tau xy is 1, tau xz is 1, all of them of course taken only positive values here. So all of them represent, let us say each row represent components of stress vectors acting on x plane, y plane and z plane. So these 3 are given to us, and these 3 are given to us, and similarly tau zx, tau zy, tau zz, all 9 are given to us. Looking at the other way, this is very good representation of what is given to us. We have 3 well defined planes and components of stress vector acting on x plane, for example tau xx, tau xy, tau xz are given as 2, 1, 1, and if you take the y plane, components of stress vector acting on the y plane tau yx, tau yy, yz are given as the second row, and for the z plane components of stress vector acting on z plane tau zx, tau zy, tau zz are given as the third row. Okay. Just understand what is the value given to us, what is the matrix or stress tensor given to us. Okay. Now, components of stress vector, so we will find out components in two ways, one along xyz axis which is shown here, then we will find along the normal and tangent to the plane. So, these are the values given to us given stress tensor and the normal vector is given to us, it is a new unit normal vector. Okay. Now, stress vector Tn, we have just now seen the expression as n dot tau, or in our simple understanding matrix multiplication of n and then tau. Okay. So, components of stress vector along x, y and z coordinates. Okay. The components of stress vector along x, y, z coordinates simple matrix multiplication of the n vector with the stress tensor. Okay. And usually you are familiar with I, j, k representation. Okay. What is used is remember we discussed vector can be represented as I, j, k or an ordered set of 3 numbers, that is what we have used here, ordered set of 3 numbers. Similarly, stress tensor we have that full expanded form I, ij, ik etc. Either you can write that way or what we have used is as a ordered set of 9 elements. Okay. So, similarly the components of stress vector is also taken as ordered set of 3 elements. Okay. So, simple matrix multiplication of we have the values of nx, ny, nz, we have values of all the 9 components here, simple matrix multiplication, you can use your calculator as well and get this 3 components of the stress vector, but they are along x, y, z axis. Okay. That is what is shown here. We have got the values of tau nx, tau ny, tau nz. Tau nx is 2.33, tau ny is 2, tau nz is 3. Okay. We can represent in the usual way, our unit vectors are I, j and then k, and use the corresponding components 2.33, 2 and 3. Okay. Now, this is the first step, okay, where we related the components of stress tensor to components of stress vector along x, y, z axis. What is our objective is shown here, we have to find out along normal and tangential directions. So, next step is to find components of stress vector normal to plane, that is one component which is a normal stress, and tangential to the plane, 2 components of them are there, they are the shear stresses. Okay. Now, we have got a vector, we want component along a particular direction. Simple, what we should do, just take projection of the vector along that direction. Okay. This we have already done. If you recall back when we discussed about Reynolds transport theorem, so integral balances etc. Remember we had a, let us say an outflow surface, and then we had a normal to the surface, and then we had velocity vector along some other direction. This is n vector and this is v vector. What did we do? We took v dot n, which means that we are taking a component of v vector along the normal, So, to find projection of any vector along some other direction, it is enough if you just take a dot product of the vector with the direction vector. That is what we have done here. We wanted, when we say v dot n, it is component of v along the n direction. So, we were interested in getting what is the velocity along this normal direction. So, we took a projection of this. Similarly, here we have one stress vector, we have the components of that, but we want components of the stress vector acting along some 3 directions. So, we have to take a dot product of this vector with the direction vector, which means that now if you find out the 3 direction vectors, this is nothing but the stress vector. If you have vectors for all the 3 directions, just take dot product. Okay, that is what we are going to do now. This step is simple, taking dot product. What we are going to discuss now is what are the 3 direction vectors along n, s1, s2. Okay. Okay. So, just to put it very clearly, we have evaluated tau n x, tau n y, tau n z. We want to evaluate along the normal, which is tau n n, and then other component is along s1, tau n s1, another component is tau n s2. Right now what we are doing is we are going to find out what is n vector, what is s1 vector, what is s2 vector. If you know that, simple dot product of this stress vector with these vectors, direction vectors, will give you the components along normal and the tangential directions. Among this, n is already known, n is given to us. Okay. So, what is objective? To find unit vectors along normal and tangential directions, that is the objective. Once you do that, simple dot product. Okay. Okay, now unit vector along normal is given to us, because that is a plane we are given. So, n is given to us. Now, we have to find out the tangential directions. Now, recall back that when we introduce this coordinate system, we introduce that as a orthogonal coordinate system. Okay. N is normal to the plane, s1, s2 on the surface of the plane, all these 3 directions form a orthogonal coordinate system. Okay. And we will use this to find out s1 and s2, to find unit vectors along tangential directions. That is the objective right now, because n is known to us. Now, the 3 unit vectors form orthogonal coordinate system, which mean, what does it mean? The dot product of these vectors in pair should be 0, n dot s1, s1 dot s2, s2 dot n, all should be 0. Okay. Let us call s1 vector as a1, a2, a3, those are the components which I have to identify, and then s2 vector as b1, b2, b3, which are the components to be identified. Okay. Now, if you see, there will be 1 degree of freedom, which means that out of 6 components, 1 can be arbitrarily specified or should be specified, and we take one of the components to be 0. Here we have taken a2 to be 0. Okay. Now, we will find out s1. How will we find out s1? As we have discussed now, they form orthogonal coordinate system. So, s1 dot n should be equal to 0, because they are perpendicular to each other. And if you take dot product of s1 and n, here you have n vector here, here you have s1 vector here. So, we will have 2 by 3 a1, next term is 0, then you have 2 by 3 a3, that should be equal to 0, which means that a1 should be equal to minus a3. Now, remember, s1 is a unit vector, which means that a1 square plus a2 square plus a3 square should be equal to 1, a2 squared is 0 and a1 squared is equal to a3 squared. So, we have 2 a1 squared is equal to 1, giving us a1 as 1 by root 2, and of course, we have already shown that a3 and a1 are opposite each other in terms of sign. So, a3 should be minus 1 by root 2, okay, which means that we have found out what is the s1 vector, 1 by root 2, 0, minus 1 by root 2. In terms of decimals, it is these values, okay, 0.7 roughly, 0 minus 0.7. Okay. Okay, now we have to find out the s2 vector. Okay. To find components of s2. Now, once again we will use the fact that all 3 form a orthogonal coordinate system, and s2 is perpendicular to both n and s1. So, how do you find out s2? Simply as the cross product of n and s1. Okay. We know that a cross product, the result of a cross product is perpendicular to both the vectors. So, n cross s1 in this case, which is s2, is perpendicular to both n and s1. So, we will use this fact to find out s2. Okay. Okay. So, now we will express this in terms of the components. We have taken S2 as B1, B2, B3, and the cross product we will use our usual determinant way of expressing the cross product I, j, k. Components of n are 2 by 3, 1 by 3, 2 by 3, S1 are A1, A2, A3. We have found out already what is A1, what is A2, what is A3, of course A2 was assumed. So, now let us find out component wise. Ith component on the left hand side is B1, ith component on the right hand side is 1 by 3 A3 minus 2 by 3 A2. Substitute the values of A3 and then A2 and then get result of minus 0.236. This is ith component of S2 vector. Similarly, for B2 of course you have negative sign extra there, and it is 2 by 3 A3 and then minus 2 by 3 A1. Substitute the values, get the result as plus 0.943, and then similarly the kth component on the z axis is 2 by 3 A2 minus 1 by 3 A3 minus 0.236. Okay. Of course, many of us would have used about cross product, used it in moments etc. It is another example where we are finding one direction is perpendicular to two other direction using cross product. Okay. Another I would say application of cross product. Okay. Yeah. So, now we have determined S2 vectors. Okay. So, let us summarize all the results whatever you have got. Just one more step is left out. We have found out all the unit vectors along normal and tangential directions. Let us list them. N was given to us, written in terms of decimals here. S1 vector we found out. We also found out the S2 vector, and then as we have discussed earlier, simple dot product of stress vector with these direction vectors will give you the component along n S1 S2, and that is what we are going to do now. Component of vector along a direction, just repeating what we have discussed earlier, is vector dotted with direction vector. Want to emphasize that the dot product. Okay. So, the stress vector is in terms of XYZ component is 2.332 and 3, that is what is written here. And so, tau and n, what is tau and n? The component of stress vector along normal to the plane, or the normal stress acting on the plane. What is that? Tn, the stress vector dotted with the direction n vector, simple dot product. We have T n vector here, we have n vector here, take a simple dot product, you will get 4.22. Okay. And then tau n S1, so take the dot product of now stress vector with S1 vector, okay. And this is Tn vector and this S1 vector, simple dot product, okay, will give you minus 0.471, okay. And tau n S2 dot product of stress vector with the S2 vector will give you 0.629. So, now we are able to express the stress vector in terms of components along normal and tangential directions. Look at the way we expressed Tn here in terms of I, j, k, they are the unit vectors. Here the unit vectors are n and then S1 and then S2, and the components are whatever we have found out right now, 4.22 minus 0.471 and then plus 0.629. Okay. So, that was what we required. We wanted the components of stress vector along the normal to the plane and along the direction tangential directions, and this is the normal stress and these two are the shear stresses. Only these are the normal stresses and shear stress acting on the plane. That was our objective. We have done a complete cycle, I would say. When we began with solid mechanics, this is a diagram we saw, okay. then we went to XYZ components, then we went to the 9 components, then now we come completely in the reverse direction, 9 components, XYZ components, and then components along N S1 S2. Okay. In terms of discussion we came in the forward direction, in terms of application we go in the reverse direction. Okay. That should be kept in mind. In fact, now only we will have a clear idea of where did we start, where did we start, where did we end, how to connect, etc. Okay. Now there are so many terms on stress. So I think it is time to summarize them so that you have a clear understanding and you really mean what you mention. So far casually you would have talked about stress, that could mean average, that could mean a vector, that could mean tensor. Okay. So this stress with 9 components, the stress tensor, remember all are at a point, stress tensor, it has 9 components, each of them you call them as components of stress tensor, okay. And the diagonal components are normal stresses, okay, tau xx, tau yy, tau zz, because they are acting normal to the respective planes, x plane, y plane, z plane. Off diagonal elements are all the shear stress components acting on the respective planes, x plane, y plane, z plane. Okay. And now Tn is the stress vector acting on any plane, moment you see n, it is of course represents any plane. And now this stress vector has components of stress vector, those components can be two ways, tau nx, tau ny, tau nz along x y z axis, or it could be tau nn, tau ns1, tau ns2, which is what we are interested in as the normal and shear stress acting on any plane. Okay. So that kind of summarizes what we have discussed in terms of terminology. Okay. Okay. Remember where did you discuss this? Where did you discuss? Ocean, yeah, ocean problem. Okay, when we discuss ocean problem on ocean, applying the continuity equation to estimation of downward velocity in the ocean, we discussed this coordinate axis. So the first one is something very familiar to us, and if you switch this x y z twice, then you get this coordinate axis now, and then we discuss what is the advantage, etc. You may be wondering why this coordinate axis now. Reason is very simple. I am going to show all the results using 3-dimensional graphs using MATLAB, and MATLAB uses this coordinate axis default. With lot of difficulty or some effort it can be changed, but just because to be easy and then so that you can also try to reproduce in the results, I am just presenting the way in which MATLAB presents, and that coordinate axis what is shown here. Okay. That is why just recollect showing these this 3 coordinate axis. So what we will see is whatever we have seen in terms of numbers and vectors and set of elements, matrices, etc., we will see pictorially in terms of 3D representation. First, all our attention on the plane and the normal to the plane. So that is the first graph. What we are seeing here is xyz coordinate axis, and the plane is shown, and of course the plane is shown so large, always imagine it is a very small plane, it is a point. Okay. And we are given the components of the normal to the plane, and so the plane and the normal to the plane are shown here. Okay. Our objective is to find out normal stresses, normal stress and shear stress on this plane. Okay. That will be the final diagram, final 3D graph. Okay. In between, let us see what happens. This is the plane whose normal is x axis. So that plane is shown, and remember the x axis is here. Okay. So normal to that plane is also shown here. Okay. Now remember, when the stress tensor is given, the first row represents the components of stress vector acting on x plane. So what is shown here is the stress vector acting on x plane, and those components are shown. The x component is 2, the y component is 1, z component is 1. Okay. Now, we are seeing the, in fact we are also seeing the x plane is shown, stress vector in x plane is shown, the components are also shown. Of course, these components are along x y z axis. Now, analogously this is the y plane and the normal to the y plane is shown. Of course, we should understand that this is the y axis. Okay. So, that is why this is the y plane and the normal to the y plane is in facing something away from us. Okay. Now, similarly the second row represents the components of stress vector acting on the y plane. So, this is our y plane and the stress vector acting on y plane is shown and the components are shown. This is the x component, this is the y component and this is the z component. Okay. Now, similarly z plane of course very easy to see because something like the floor, and the normal to the z plane is also shown, and the last row represent the components of the stress vector on z plane, and the components are along the x axis 1, y axis 1 and z axis 3. Now, we have seen the representation of the information given to us, that is all we have done. Now, what did we do? We applied the Cauchy's formula and found out the components of stress vector along x y z axis, and that is what is shown here. The plane is shown here and then the normal vector to the plane is shown here and the stress vector acting on the plane is also shown. Now, what else is shown? The components of stress vector along x y z axis is shown. What is the component? 2.33, and that is what you see here. Of course, you do not see as 2.33 because of the angle of view. Okay. And then along y axis you have 2 here and then along z axis you have 3 here. Okay. And so, this is a representation of our intermediate result, that is the result which you obtain after applying Cauchy's formula, gives the components of stress vector but along x y z axis. Now, the final result. Now, let me explain what is shown here, the plane certainly, and then first let me explain the axis. Axis important is for this figure are the normal and the tangential directions. So, the normal to the plane is shown here, the first tangential direction S1 is shown here, second tangential direction S2 is shown here. Now, the stress vector acting on the plane is shown by this yellow arrow mark. What I have shown here is the representation which used in the previous slide in terms of x y z axis. More importantly, what is you see here is a representation of the along in terms of components along our chosen coordinate axis which is attached to the plane. That is why you see here n, S1, S2 here. Now, let us look at the components. 4.22 acts along the normal. So, this is the normal component of stress vector, that is a normal stress. Then minus 0.471, this is the direction, but it is minus 0.47, that is why you have along the negative direction to S1 is along this direction, because we have minus 0.47 it acts opposite to that. Finally, you have S2, this is the S2 direction tangential vector, the value is 0.629 and that is what you see in the magenta color. Okay. So, we have shown the plane and then the 3 coordinate directions, and then we have also shown the stress vector and also shown the normal stress component and the shear stress components. Okay. Of course, the arrows are not sharp, I made them very thick so that becomes easy to visualize.